Reactants and products are just generally in their gas phase. If they're in their gas phase, we can take it up a notch, so to speak. Then we can talk about another equilibrium constant expression in terms of something that's called Kp. Okay. So what this says, all this blah blah, says that, well, I'll go ahead and do it this way, if it's okay with you. I'm going to say that I'm going to say these are all gases. It happens a lot. A and B are gases, C and D are gases. If that's the case, then we can come up with what we call a Kp expression, and that will be equal to, like it says, the partial pressures of the reactants. So I'm going to go partial pressure of C raised to its stoichiometric coefficient times the partial pressure of D raised to its stoichiometric coefficient divided by the partial pressure of A raised to its stoichiometric coefficient. Also in the denominator is the partial pressure of B raised to its stoichiometric coefficient. That's it. That's it. Kc and Kp will have different values, but here at the end, I'm going to kind of relate the two. Okay, so this is what I just did. Isn't it funny how the letter C, the capital C, and the lowercase c like look the same? Like, what's up with that? They just do. Okay. So K, we could have a Kc, molar concentration, we could have a Kp. And it deals with the partial pressures of the products. It's always products of reactants. Products raised to stoichiometric coefficients by reactants raised to their stoichiometric coefficients. So here's the deal. The pressures need to be in units of atmospheres. Okay, and then the units actually kind of cancel out, like I showed you before. Units of atmospheres. So for the same equilibrium, there's got to be a relationship between Kc and Kp. I'm going to kind of talk you through that. Now, whether you like this proof I'm going to do or not, I'm going to show you the derivation of something that's going to have a blue box. Blue boxes are things you use. Proofs are not necessarily. So we're going to consider this equilibria that I have up on the board, kind of a box cutter equilibria. Okay. Well, going back to the ideal gas law equation, PV is equal to nRT. We can actually get molarity if we take the N over the V term. So we can rearrange that N over V. That's moles per liter, so that's molarity, right? All right. So we can take this quantity, which is molarity, and substitute it into our equilibrium constant expression, the normal Kc version. And here's what that looks like. So if for each of these quantities, the molarity of C, it's a gas, would be the partial pressure of C divided by RT raised to, and then we have to raise it to its stoichiometric coefficient. We do it for both of the products, C and D, and then we divide by the reactants, A and B. Now, if you're used to kind of simplifying terms like, oh man, all those RTs, they go away. Not quite so fast. The problem why the RTs can't all necessarily go away is because we have RTs raised to a power, actually the inverse of RT raised to a power, the inverse of RT raised to a power. If all of those powers are the same, they go away. So you're right in that sense. So we pull out the inverse of RT term and kind of apply the power and keep the power associated with the partial pressures. That's what I've done for C and D and A and B here. Now we're going to take the RT, 1 over RT term out, and we're going to have to make sure that we bring their exponents with them. So it looks like this. We're going to gather the partial pressures. Here's the partial pressures all gathered together. We're going to have one big inverse of RT, and what it's going to be is this the power of the inverse of RT will be C plus D minus A plus B, because it's a minus here because A and B are in the denominator. So we got a mess here. but that's what it ends up being. Well, that mess up here, or this up here, this actually is what we can call the change in moles. Why? Because the stoichiometric coefficient are the relative moles. So the change in moles is simply the coefficient, C plus D minus A plus B. That's your delta N. Okay. So again, if we can get delta N is equal to 0, check this out. If this is equal to 0, what's anything raised to the 0th power? 1. This term goes away. So yeah, if there's no change in moles, if delta N is 0, then actually, as it turns out, your Kc ends up being equal to your Kp. Or I should say your Kp is equal to your Kc. Because what's this right here? This guy right here is your Kp. That's your Kp. Sorry, keep going back. But anyway, so Kc is equal to Kp times the inverse of RT raised to the delta N. Okay, and we can actually, I think I have one more cleanup step. The inverse of RT is not as slick as just RT inside itself, so we can do that if we take it negative delta N. Maybe. Blue box alert, blue box alert. So for a given equilibrium that has everything that's going to show up in your equilibrium constant expression in its gaseous state, we have either a Kp or a Kc option. And Kp, oops, big K, not little k. Kp is equal to Kc times RT raised to the delta N. And you just have to know what delta N is. It's your this plus this minus this plus this. All right. The value of R we're going to use is the one that we used for the ideal gas law equation. That's at 0.082058 liters atmospheres mole per Kelvin, liters atmospheres per mole Kelvin. And like I said before, we need our pressure to be in units of atmospheres. So let's work a problem, shall we? Right off the bat, can you see what what's our delta N here? 1. It is 1. Very good. And delta N's can be negative or positive. Yeah, but 2 minus 1 is 1. You got it. So we're given Kp here, and we're supposed to knock out Kc. Well, we can do that. I can't remember, is this, remember, I didn't screw up, but remember I gave you an equation sheet for your last unit exam, and it had extra stuff on it? I can't remember if this was on there or not. I know. Maybe just have to remember this. Yep, you guys told me delta N is 1. You guys got it. The temperature that we're running here is, oh yeah, we do need the temperature, don't we? Because RT. That has to be in units of Kelvin, so we take our 45 Celsius, add 273 units, get 318 Kelvin. Now ready to plug and chug. We have to rearrange it solving for Kc. Kc is equal to Kp divided by RT raised to the delta N power. So Kc is equal to 0.62, that's your Kp, divided by the ideal gas law constant, 0.082058. Also in the denominator is your temperature, 318 Kelvin, all raised to the first power. It's weird to see like no units, like really? But we talked last Friday, or a week ago Friday, that units of Kc is unitless. So round to 2 sig figs, I get a value for Kc from that Kp of 0.024. That works. Now I do this. Okay. So it just worked out nice that you're going to have 3 parts to work. And oh my gosh, did I work problems this break? And I'm like some of you guys, I waited till like Saturday to start doing my homework. So I'm like, oh my gosh. I worked a lot of problems. But I posted things already to Canvas. I finished Unit 3 and started Unit 4. So, all right, on to Part 2. Here we go. This sort of stuff kind of reminds me of Hess's Law. If you liked Hess's Law, you'll like this stuff. If you didn't like Hess's Law, you probably won't like this stuff. So there are times when we want to take the equilibrium and we want to do something to it. Like we want to scale it down by dividing all the coefficients by 1/2. And it's going to have consequences for your KC, and we're going to talk about that. We want to double everything. It's going to have consequences for your KC. We want to add equilibria, then you do something with the KCs, okay? So, for instance, if we look at this sulfur combined with oxygen to form SO3. So this is balanced, right? Balanced equilibria. We could come up with your equilibrium constant expression, and it would look like this. Notice I'm going to go ahead and add a little 1 subscript. Stay organized. So I'm going to call this equation 1. That's what that is. Call this 1. And notice then I have the equilibrium constant 1. That's what that 1 means. Well, I'm going to scale it. Looks like I'm going to multiply through by 2. Okay, so then this is also balanced, but it gives us a new equilibrium constant expression. We'll call that 2. And this is your equilibrium constant. 2 is equal to, so why aren't I including s, like s squared down here? Because it's a solid, yep. And as it turns out, would you probably buy this, that it looks like this down here is the square of this? Doesn't that look right? This quantity, if I square this quantity, I get this quantity. And to get this down here, I took it times 2. So that's kind of actually going to be the law of it. The second one that I got, multiplying through by a factor of 2, actually is your first one, your first equilibrium constant, raised to the 2nd power squared. So that's kind of nice. So here's the rule for manipulating. If you multiply through by some constant factor, then your new KC will be your old KC raised to that power. Makes sense. Here's another one. And this one's pretty intuitive, I think. It looks like we're picking on number 2. Okay, so we could write our equilibrium constant expression would look like this. The beauty of chemical equilibria is they go from left to right, and they also go from right back to left again. So we could swing it around the reaction arrow, put your SO3 on this side, reactant side, instead of product side, and here's these guys. And if we rewrite the, if I call that 3, if I write now the new equilibrium constant expression, you know, it's the flipped version, isn't it? The relationship between these two is the inverse. So that's the rule, basically. If you swing it around the equilibrium reaction arrows, then your new KC will be equal to the inverse of your old KC. Makes sense. I like when things make sense. So those are two rules. There's one more thing I want to talk about. What's that trick? And you guys might need to go back and forth between a couple slides, because this makes more sense going back and forth between a couple slides. So in Hess's law, remember we added equations. And what you do is you cancel things like, you know, it wasn't even just Hess's law. We did it in mechanisms too, didn't we? Like the CO gas would cancel, CO2 would cancel. Looks like then what we end up with is we bring down our Fe and our H2O, and then the product side, we bring down our FeO and our H2. We're just adding them. So like I said, you can kind of flip back and forth between these two. So the equilibrium constant expression for the first one looks like this. Okay, remember the solids don't appear. And the equilibrium constant expression for the second one looks like this. And the way this works is if you were to take these two quantities, I'll draw them. If you were to take these two quantities and multiply them by each other, check this out. The CO2 cancels, the CO, you know, have to be raised to the same power. They both cancel. Okay. If we take those two and multiply them by each other, we actually get this H2 over H2O, which coincidentally is what the third equilibrium constant expression would look like. So the third equilibrium constant expression we know is the molar concentration of H2 divided by the molar concentration of H2O, which we can see actually is K1 times Kc1 times Kc2. So in blue it says that if you add two chemical equilibria together to get a third chemical equilibria, or maybe have 4 or 5, I don't know, add them all together, then if you multiply all of their Kc's, you get the Kc of your... Now someone tell me why H2O shows up. Oh, it's a guess. Thank you. I feel better. Okay. So to show you those in action, we're going to do an example of ammonia in equilibrium with its element or molecular nitrogen and molecular hydrogen. You'll see the chemical equilibrium here in a minute. But I'm going to tell you that, well, let's just go ahead and put it up here, because this is kind of confusing. See if I can make sure I balance it. So here it is unbalanced, N2 plus H2 in equilibrium to form NH3. Let's go with a 2 there, maybe 6. That looks pretty good. Something like that. We're going to go ahead and say lots of time. The significance of lots of time is I'm allowing this chemical equilibrium to do its thing. So at equilibrium, because one of the last things I want to talk about is not everything of interest is at equilibrium. So at equilibrium, we have these molar concentrations of ammonia. NH3, molar concentration of the product, as written here, anyway, 0.16 molar. Molar concentration of the N2 is 0.030 molar. Molar concentration of the H2 is 0.037 molar. Now my point is going to be that whether I write it like this or whether I write it like this, I took it times 1/2, right? Or whether I write it like this, reverse it, these equilibrium concentrations are the real deal. Okay, this is just how I write it. This is the real deal. So it's going to have to work to give us the same quantity with these different Kc expressions. So if we write so we're going to do these three here, which are probably kind of like when I wrote up on the board, I'm not sure. We're going to actually use these equilibrium concentrations. First, we're going to write the equilibrium constant expression, and then we're going to use these equilibrium values to come up with a Kc for that one. We're going to do it for this one down here where we reverse it, and then we're going to do it down this one where it looks like we take the reversed one and take it through by 1/2. And we'll have different Kc values with the same equilibrium concentrations, but our Kc's, 3 Kc's will be related just as I said. Okay, so here we go. First one. Equilibrium constant expression would look like this. Okay, so it's the molar concentration of the product, NH3 raised to the second power, divided by the molar concentration of N2 raised to the first power and H2 raised to the third power. And so all I'm going to do now is to substitute these quantities that are given at the bottom of the slide into there, and it looks like this. So Kc is equal to 0.016 squared divided by, in the denominator we have 2 terms, 0.030 raised to the first power, also in the denominator 0.037 raised to the third power. Looks like 2 sig figs, and we get a value of Kc for that one is 1.7 times 10 to the second. Cool. That's great. So that's the first one. The second one, we're going to reverse it. And one of the things we said before, if you reverse it, then the new Kc is going to be the inverse of the old Kc, right? So we're going to check that. If we reverse it, we come up with a new equilibrium constant expression. So now Kc2 is equal to molar concentration of N2 raised to the first power, the molar concentration of H2 raised to the third power, divided by the molar concentration of NH3 raised to the second power. So this is my, I'll put a little 2 there. We substitute in the quantities that we have at the bottom here, and that ends up with 0.030 times 0.037 cubed raised to the third power in the numerator. In the denominator, there's only one term, 0.016 squared. Round it to 2 sig figs. I end up with 0.0059. Which, if you check it out, these are the reciprocal of each other. What politician has been fixated on the word reciprocal in the last 4 months? Reciprocal. Isn't that cool? All right, last one. The last one actually looks like it takes 1/2 of this right here. So we can write the equilibrium constant expression for our Kc3. H3, oops. I know it feels weird to take things to the 3/2 and 1/2 power, but, or not so much the 1/2 and the 3/2 power, yes. So substituting in the quantities, this is what we come up with, 0.030 raised to the 1/2 power times 0.037 raised to the 3/2 power divided by 0.016 raised to the 1st power. And we said if you're multiplying through by a factor of 1/2, right? Then this guy right here, this is my 2, these are order. This guy should be, it should be K2 raised to the 1/2 power. Does that seem right? So round to 2 sig figs, you get 0.017, which is, if you take 0.0059 and raise it to the 1/2 power, or take the square root of it, it is, I don't know, that's real messy up there, but. So that's just kind of a proof. Any questions about that? So you'll have some go with that in this homework. One last section. And this is why I added little e's here, because these are at equilibrium. Okay? We're stepping out, and I call it a snapshot. We're stepping out and not necessarily at equilibrium. We're gauging the molar concentrations of the reactants and products in a soup of reactants and products. And that's what we call the reaction quotient. It's a snapshot. Now, one thing about snapshots is sometimes they look good, sometimes they don't look good. Thank goodness for digital. Okay. Notice that your reaction quotient QC, it takes the same form as your equilibrium constant Kc. It's calculated the exact same way. So one important value of QC, guess what? If QC, the reaction quotient you come up with, if that's equal to your Kc, you are at equilibrium. You have arrived, because it can happen, it does happen. So actually, I'm going to kind of talk you through some scenarios, but the reason there is something called reaction quotient is that we need to gauge a mixture of reactants and products, and then basically test our QC, compare our QC to our K from our Kc. In comparing, we can see if it's at equilibrium. I told you if they're equal, then it's at equilibrium. If it's not, then the other thing is we're going to start kind of saying, if it's not at equilibrium, which direction does it need to go in order to reach equilibrium? I'll kind of describe that. So that's an important part of the test. So here is our generic 2 reactants go to form 2 products. Again, your reaction quotient expression looks just like your equilibrium constant expression, just like it, except instead of Kc, it's a QC because it's a snapshot. So we have 3 different scenarios. First scenario, your QC or Q is equal to K or Kc. That's it, you're at equilibrium. Okay? You're done. The other 2 scenarios is one is it's less than, your reaction quotient QC is less than your Kc. And then the third one is that your Q is greater than your K. Now, if your Q is too small, you're like, oh man, it's too small, what do I do? Well, I need more products if it's too small. So that's actually what's going to happen. If your QC is small relative to your equilibrium constant Kc, then some of your reactants are going to have to proceed to form products to reach equilibrium. There's some things in science where I don't memorize things. I know I've said this before. I just like think through them, and this is one of those. I just write it and I think through it. So the third scenario, so we have QC is equal to KC, QC is less than KC, where it will have to go to form products to reach equilibrium. The other scenario is that your QC is too big. So if your QC is too big, then that means I have too much products. And remember, the beauty of a chemical equilibrium is it goes from left to right, like we're used to, and it also goes from right back to left again. In this case, what you're going to have to do to reach equilibrium is some of your products are going to have to go back to form reactants. And that's where it's kind of like, you know, in normal chemistry, we don't think of it going from right back to left again, but that's exactly what's going to happen in order for it to reach equilibrium. And kind of an underlying theme of chemical equilibria is they want to be in equilibrium. They want to be in equilibrium. So this, if the word is spontaneous, it will be a spontaneous sort of process. It will go from products back to reactants. If Q is too big, it will go from reactants to products. If Q is too small. If Q is equal to K, then it'll be like, it's dynamic, right? So, but for every little bit it goes in the forward direction, it will also go that same rate in the reverse direction. All right, so I've got some figures to kind of show you what that might look like. In this case, if we only have reactants present, and then actually you're going to have 0 divided by something, and 0 divided by something is 0, right? So your Q is going to be too small. And like I said, if it's too small, it's going to have to go to form from left to right. It's going to have to form from reactants to products. And no choice. Then here's we have, remember we said that when, here's the two reactants, green and red, and the product is yellow. So you kind of see yellow building up. Here when it's got a steady molar concentration, which it's showing it there, it looks like it's here. I don't know. Well, but equilibrium is going to reach. This is actually showing your reaction quotient QC going from 0 up to some value until QC is equal. Well, in this case, it's the same equilibrium, but notice that we have all product, but no reactant. So it's, and this one hurt my brain when I thought about it. So in this case, we have some number divided by 0. Some number divided by 0 is infinity. But bottom line is it's too large, so it's going to have to go from products back to reactants. And they'll reach equilibrium. Okay. Oh yeah. Okay, so let's take a look. I might would draw a picture of this. So we have chemical equilibrium between H2I2 goes to form HI. And here's my box. And it says that initially they went ahead and they were kind of lazy and made the molar concentration of everything 0.002 moles per liter. So that means the molar concentration of H2, molar concentration of I2, molar concentration of HI. It's all equal to 0.0020 moles per liter. And it went ahead and gave the temperature. That was nice of it. Because we need it. 190. And it said that the Kc is equal to 46. So bottom line, what you're going to see down here is we come up with a QC and we compare it to Kc to see what's got to happen. Is the system at equilibrium? Well, if our QC, or reaction quotient, equals 46, yeah. If not, then which direction does it need to go in order to reach equilibrium? Well, it depends on if it's larger than 46 or smaller than 46. So can you see why in this case we need to use a reaction quotient? Oops, sorry. I'm kind of surprised it didn't. Is this in your notes? I would come up with a QC, I'll kind of move this so I have more room, is equal to HI raised to the second power divided by H2 raised to the first power, also raised to the first power is I2. So all I'm going to do is substitute those quantities in there. And the math's pretty easy, isn't it? Wow. Check that out. You end up with the lower concentration of HI, 0.0020, raised to the second power. In the denominator, we have the molar concentration of H2, 0.0020. Also in the denominator, we have molar concentration of I2, 0.0020. What's that equal? 1. They all cancel. Isn't that pretty? Given it 2 sig figs, 1.0. So now we can actually answer our question about it's not in equilibrium, right? And which direction it's going to go. It's too small towards products. Yep, you got it. Well, there was my, one of my bills in the back of it. I was getting ready for today's lectures, you know, free back to back. I don't know if I would suggest that for anybody, but and then there's that 10 o'clock. Carl, I'm like, what do you think? How far can you? He's like, oh yeah, you can do all 3 parts like that. So he's right. Okay, so yep, here we go. It's not an equilibrium because they're not equal. And just like you told me, the fact that it's too small or smaller means that reactants must be converted to products to reach equilibrium. You've already heard me this afternoon, sometimes I'll say it'll go to the right. That's the same thing as reactants must be converted to products. Go from left to right. Same thing. So these 2 figures I've shown before, and I think when I showed them before, I'm like, well, if I had time or took the time, and I'm still not going to take the time, but this is something they call the water-gas shift reactant. Water-gas shift, it's kind of weird, I never heard of it. Anyway, but we have 3 different scenarios. In this case, notice, and this is color-coded, it looks like we have all reactants. We have all reactants here. The second case, we have all products. The third scenario, we have reactants and products. So you can see. Clearly not an equilibrium, because I could go ahead and write a QC expression and plug in these molar quantities, and it's not the same number. This is before you allow it to establish equilibrium, and this is at equilibrium. So at equilibrium, notice that I just think equilibrium are so cool. Actually, this last one, is it the same? Why don't you think? No, it's different, isn't it? My point, I guess, would be, and I'm not going to do because I don't feel like it, but we could take these quantities and plug them into the QC, the reaction quotient expression, and we come up with the same number for each of these. Okay. Ta-da! Part 3, parts is parts. Glad it's you, not me, but we aren't meeting Wednesday, so. our meeting Thursday. Oh, that's right. So Thursday for lab, we're doing, the title says something about the Chatelier's principle. So we are doing the one that was scheduled. And so I'm going to have to, since we haven't covered that yet in lecture, it'll work out fine. Just come and we'll talk about it and turn you loose. And it's a fun experiment, series of experiments.